Alright, in this video we'll be talking about sound waves and a very important property of sound, which is reflection. Now first, sound is a form of energy produced by vibrating bodies. Sound is a form of energy produced by vibrating bodies. That means we usually get sound when we have a vibrating body or when a body vibrates. Now example, when we strike a tuning fork, its prongs vibrate. This is what a tuning fork looks like. Alright, if you strike the tuning fork, the prongs, these are the prongs, okay, they vibrate. Now these vibrations give rise to sound waves. Now propagation of sound waves. Sound waves are propagated through air by the displacement of air molecules. That's how sound travels in air. They, are, they travel in air, or they are propagated through air by the displacement of air molecules. The molecules vibrate in a direction parallel to the direction of travel of the waves. Okay, that's why sound is classified as a longitudinal wave. Sound is a longitudinal wave because the vibration of the particles occur in the same direction of the wave, or you can say parallel to the wave. The vibrating particles move in a direction parallel to the direction of the waves. Okay, so sound, do not forget, is a longitudinal wave. Now, velocity of sound wave. The velocity or the speed of sound can be defined as the distance traveled by sound in 1 second. How far or how much distance can sound cover in 1 second? That's what we mean by the velocity of sound. Now, usually we see a lightning flash before the accompanying sound of thunder because light travels faster than sound. This is a very important concept you also need to have at the back of your mind. Lightning flash, we usually see lightning flash because light travels faster than sound. Now, mathematically, the velocity of sound is given as v equals f lambda. Alright, don't forget the velocity or the speed of sound is the distance traveled by sound in 1 second. Most times, we usually use velocity and speed interchangeably because we're just concerned about the magnitude of the sound. Alright, so that's it. And mathematically, the velocity of the sound is v equals frequency times wavelength, where v is the speed or the velocity of the sound, f is a frequency, and then this is wavelength. Okay, so don't forget, this is the formula for calculating the speed or velocity of sound. Now, reflection of sound. The reflection of sound waves is known as echo. All right, reflection of sound. Echo is what we call reflection of sound. This is a very important property of sound waves. All right, so the reflection of sound is known as echo. Now, when one stands in front of a wall and claps the hands, the time which elapses before the echo is heard depends on the distance away from the wall. You have an individual standing in front of a wall, and then this individual here claps his or her hands. The sound travels and then is reflected back. All right, so it said when one stands in front of a wall and claps their hands, the time which elapses before the echo is heard depends on the distance away from the wall. So we have the distance to be d. So the time it will take for this sound to be reflected depends on the distance. If the distance is very close, it's going to affect the time taken for the sound to be heard back, or for the sound to be reflected. If it's very far, it's going to take so much time also for it to be reflected back. All right, so that is what we mean there. Now, that time that will elapse, mathematically, this is the formula. Okay, this is the formula here. We have the time equals to the total distance traveled divided by the velocity of sound. The total distance traveled, if the distance between the wall and the individual is d, the total distance traveled will be 2d, because the sound is going to travel to the wall and is going to come back or move away from the wall back to the individual. So we have d going, d coming, and that will give us d plus d, which is 2d. So that's the total distance. All right. So don't forget, this is the time that will elapse, and it is equal to total distance traveled by sound all over velocity of sound. The total distance is 2d over v. So whenever you're looking at echo, please don't forget, whenever you're looking at echo, the time, all right, taken for the sound to be heard back is equal to 2d over v. This is the formula for calculating the time that will elapse whenever you have a case of echo. Now, here they said the continuous occurrence of echoes due to multiple reflection of the original sound is known as reverberation. Reverberation is a continuous occurrence of echo due to multiple reflections of the original sound. Now, suppose a reflecting wall producing the echo is d meters away, like we have here. The time taken to hear the echo is this. Don't forget. So this is our formula for echo. Now, example 1 here says a man standing 510 meters away from a wall sounds a whistle. So d is equal to 510 meters. Sounds a whistle. So the echo from the wall reaches him 3 seconds later. So this is a case of echo, don't forget. Reaches him 3 seconds later. They say calculate the velocity of the sound in air. So because it's a case of echo, we use the formula T equals 2d over v. That's the time taken to hear the echo divided by 2, the total distance traveled, which is 2d all over v. How do we know it's a case of echo? It was mentioned there. The echo from the wall, so it's a case of echo. If they don't mention it as echo from the wall, they can say the reflection of sound. You see the same thing, right? So we have T equals 2d over v, and T is 3 seconds. So we have 3 equals 2d, d is 510. So we have 2 times 510 all over v. And that will give us uh, 3 times v. That will give us 3v. If we cross multiply, because we're looking for v, 3 times v, 3v equals 2 times 510. 2 times 510. So to get v, we divide both sides by 3. So we have 3v over 3 equals 2 times 510 over 3. That will give us 10 divided by 3. That will give us 340. So this will cancel this. So we have v to be equal to 340 meters per second. So that's our answer here. Now, looking at this question, it says how far from a cliff. So we're looking for D now. How far from a cliff should a boy stand in order to hear the echo? It's a case of echo again, so we use the echo formula. How far from a cliff should a boy stand in order to hear the echo of his clap? 0.9 seconds later. So we have T to be equal to 0.9 seconds. And then they gave us speed of sound in air, V, to be 330 meter per second. So how far is the distance? It's a case of echo, so we need to use our echo formula, which is T equals 2d all over v. So T is 0.9 equals 2d all over v, which is 330. We're looking for d, so we need to cross multiply. So that will give us 2d times 1. That will give us 2d equals 0.9 times 330. 0.9 times 330. So to get d, you divide both sides by 2. So we have 2d all over 2 equals 0.9 times 330 all over 2. So this will cancel this, and then you have d to be equal to, you have 0.9 times 330 divided by 2. That will give us 148.5 meters. Now for this question, it says a man hears his echo from a nearby hill 2 seconds after he shouted. Right? So the man hears his echo from a nearby hill 2 seconds after he shouted. So the time is 2 seconds. You see, if the frequency of his voice is 260 hertz. So we'll bring out the value of the frequency, which is 260 hertz. And the wavelength is, give us wavelength also to be 1.29 meters. How far is the hill? So we're looking for D. So this is a case of echo. All right. Man hears his echo from a nearby hill 2 seconds after he shouted. They say, how far is the hill? So for a case of echo, we fall back to our echo formula again, which is T equals 2D all over V. All right. Now looking at this question, T was given. We are looking for D, but V was not given outrightly. But we can get V from the frequency and the wavelength. Don't forget, when we started this course, we said the velocity of sound mathematically is equal to what? V equals F lambda. So V is equal to F lambda. F is 260. So we have 260 times lambda, which is 1.29. So that will give us V equals, we have 260 times 1.29. So that will give us 335.4 meter per second. So that's our value of V. All right, so now we have T to be 2 seconds. So we're going to say, substitute our values. We have 2 equals 2D all over 335.4. Okay, if we cross multiply, we're going to have 2D times 1, which is 2D equals 2 times this, 2 times 335.4. Now we're looking for D. We'll divide both sides by 2. So we have 2D over 2 equals 2 times 335.4 all over 2. This will cancel out this, and then you have D to be 335.4 meters. Okay, so this is the distance. You see how far is the hill, so this is the distance of the hill. Now for this question here, it says the speed of sound in air is 330 meters per second. So V is equal to 330 meters per second. This is the speed of sound in air. They say how far from the center of a thunderstorm is an observer who hears a thunderclap 2 seconds after the lightning flash. Alright, how far from the center of a thunderstorm is an observer who hears, so the time taken to hear the sound, alright, is 2 seconds after the lightning flash. And they said neglect the time taken by light to travel to the observer. Now, is this a case of echo? This is not a case of echo because it was not mentioned in the question that the sound was reflected. Or, yes, it was not mentioned in the question that the sound was reflected. All right, or we have echo here. So it is not a case of echo. What we have here is sound traveling from the center of a thunderstorm. Let's say this is the center of the thunderstorm. They say how far, the speed of sound is 330 meters per second. Now they said how far from the center of a thunderstorm is an observer. So the observer is far away from the center of the thunderstorm, who hears a thunder clap, okay, 2 seconds after the lightning flash. So for a thunderstorm, we have both light and sound traveling, but light travels faster than sound, so sound is behind. All right, now the observer hears this sound 2 seconds later. That's time taken for the sound to travel is 2 seconds. Okay, now they are asking us for how far is an observer. Okay, here's the question: how far from the center of a thunderstorm is an observer? Okay, so we are looking for the distance between the observer and the thunderstorm D. Okay, and then they give us V, being the speed of sound, to be 330 meters per second. The time taken for the observer to hear the sound is 2 seconds. So we just go with our normal equation for velocity, which is velocity is equal to distance or displacement over time. All right, this is not a case of echo, so we cannot use today. We don't have the sound reflecting back. Okay, so this is what we have. So we have 330 equals d over 2. So we cross multiply. And that will give us d to be equal to 2 times 330, which is 660 meters.